Okay, so we're going to get back into chapter 13. We're going to wrap it up. To review for you, we looked at the excitation-contraction coupling in a cardiac muscle and contrasted it to our smooth and our skeletal muscle. The first thing is, in figure 13-14, I tried to differentiate that in this first image, we're looking at two different cells. So I just was showing that intercalated disc where our gap junctions. You could have just as well drawn a desmosome in there to really tie in the two primary types of junctions that you would find between two contractile cells. And then yesterday I was speaking with my class and I saw this little guy over here, the T-tubules, and I was under the impression that there were no T-tubules in cardiac muscle, but I was wrong. There's, I think, just one per cell. So there is a T-tubule, but not near as extensive to, say, a skeletal muscle. So it does the same thing to affect the permeability of the adjacent sarcoplasmic reticulum. But we know that we don't have to rely exclusively on the T-tubule because we have excitation coming through the gap junction. And so that makes sense why there's not quite as many T-tubules in the cardiac muscle when contrasted to the skeletal muscle. So excitation, ions flow from one cell to another, that potential is flowing, which affects the SR. But it can also conduct down, looks like maybe just a single T-tubule per cardiac muscle cell or contractile cell. So this image is accurate. Not thinking so. So let's just review very quick. We talked about this, didn't we? Yes. Okay. So let's just put it into picture. We learned that a cardiac muscle cell is going to get excited when there's a polarity change, whether it comes from the pacemaker or if we even look at, right, say the nervous system. We'll see how that overrides in just a second. But there's going to be a potential change, right? Say, for example, the flux of sodium from one cell to another. That depolarization opens up our voltage-gated channels of the contractile cells to let which ion in? Calcium. Calcium comes in from the extracellular fluid. It can also come in from the sarcoplasmic reticulum. So that extracellular source of calcium is very analogous to our smooth muscle cells. But once calcium is available, it works like which cell type? Skeletal muscle. Because it's going to bind to troponin to pull back what? Tropomyosin to allow for that cross-bridge cycle. So calcium's available, ATP is available, etc. And then right, at some point the muscle is going to get ready to relax. And so calcium goes back to the SR, and calcium goes back to the extracellular fluid, and the muscle can relax until the next excitation comes through. That's the excitation-contraction coupling in cardiac muscle. We then, right, I think we concluded here last week, transitioning to the EKG. So I'll briefly talk about it, but reminding you, we did an EKG study in lab last week, unless you were in the Thursday lab. Okay, so half of you guys are familiar with it, half of you guys are not. The EKG, or you may say ECG, electrocardiogram, measures the surface electrical activity as a result of the heart doing its thing. So you've probably seen an EKG. Maybe you've had one taken or measured on you. But in order to do so, you have to put electrical leads in different spots of the body. In the lab that we did, we had 3 leads, so it wasn't real accurate. And you kind of go up in triplicates there. And in a hospital, I think it's up to, is it 12? I think it's like 12. Does anybody work? I think it's 12 leads that they'll put on a patient to get really accurate electrical activity. But like we did in the experiment, or would have done, is if you put the leads on backwards, invert the positive and negative leads, it reports the data backwards. So it might look like someone's having a heart attack, right, when they're not. So it's important that whoever's doing an analysis is setting up the equipment properly. And if we look at the EKG, the big thing is to remember is the EKG is not an action potential. It's a result of intracellular action potentials, but are we sticking electrical probes in someone's heart muscle? No. So we're not measuring action potentials, but we're measuring at the surface of the body. And so figure 1316 tries to overlay the cardiac muscle cell action potential shown above with the EKG that we'd measure at the surface of the body. So is an EKG an action potential? If we look at the EKG, it has unique patterns, and they're called waves. And they're numbered, labeled, I guess, sequentially. And they just go in alphabetical order, starting with letter P. And so on your handout, label the waves. We'll talk about what's happening in each of the waves. So the first is called the P wave. It points up. Then we have the Q, R, S. And the reason we put them together is because there's a lot going on at this point in time. And then finally the T wave, the last thing. So each of these, or all of these waves collectively, would be a single electrocardiogram measurement, a single heartbeat, basically. And then there's a little bit of a latent period, and then it repeats again. P, Q, R, S, T. So each one's a single heartbeat. Does that make sense? These electrical activities are really important to study, especially if someone's having heart problems or conditions or disease or whatever the case may be. If any of these waves are off, right, or not in set points, a cardiologist can diagnose different heart conditions. And so let's study what each of the waves mean. And this would be a review from your pre-lab last week. We would have completed it, but maybe didn't study it. So let's review what each of the waves represents. First, right, we've got this little GIF to illustrate physically what's happening to each of the chambers by noticing the shaded area, the myocardial cells, that either contract or relax, or we would say systole or diastole, right? And then the excitation through that chamber, highlighted in red. And then below the heart is just correlating those physical events with the electrical surface EKG pattern. So if we kind of let it reset, where does the P wave, what's happening? Which chambers are active during the P wave? The atria. Right? The SA node depolarizes, it spreads through those internodal pathways. And then we go quickly into the QRS complex, where you note that the atria relax, and the ventricles get excited and contract. I'll have it for you in text in just a moment. And then the last thing during the T wave is the ventricles relax, or we would say go into diastole, and electrically they would repolarize because they're leading them into diastole. So it's just a continual cycle. With each heartbeat, you should be able to pick up a nice little EKG sequence. Let me help you. So I'll come back to this image. We'll fill in the text to see what's going on. To review for you, during the P wave, what is happening is that SA node is depolarizing the threshold. Atria are going to both atria, so the internodal pathway, are going to depolarize to threshold. And the contractile cells, when they receive that action potential, will go into, what word do I have there? Systole. That means during the P wave, the atria are contracting and pushing blood down into the ventricles. The next thing, 3 waves are actually summed together into what we'll call the QRS complex. I'm going to pull back that word sum, though. They're not added. They're combined to what's called a complex. We're going to discuss 3 waves simultaneous in what's called the QRS complex. Well, the first thing is, if you recall from our couple of weeks of discussion about the heart, is we need the chambers to work in opposition of one another. Opposition almost sounds like a bad word, but what I mean is when the atria are contracting, the ventricles should be relaxing, and then vice versa. Okay? And so the first thing is, if the atria were just in systole, we need to make sure they first go into what? Diastole. And that's what's happening during this first part of the QRS complex. That little Q wave is when the atria are repolarizing back into, physically going into diastole. They got to relax. So atria contract, then atria relax. So P wave, Q wave, real quick. The rest of the QRS complex is those large ventricles, the interventricular septum and the outer portion of the ventricle. Sometimes people say the wall, but the outer portion of the ventricles will then begin to depolarize and fully enter into which phase? Systole. So during the QRS complex, the atria repolarize and enter diastole, while the ventricles depolarize and enter into systole. The next thing to deal with is getting those ventricles back to what? Diastole. So they have to electrically repolarize back to the resting membrane system. And these are the phases of an EKG. It happens each time, hopefully, for each of the chambers. Continuously for a very long time, for years. Right? Measure these. What questions do you have about the sequence of excitation through the, or I guess the EKG correlation with the physical events of the heart? Okay with that? All right, that's where we're going to transition to the handout, which I just gave you guys. That takes us to the conclusion of chapter 13. And I didn't get a lot of time to kind of mess with the picture, so I'll read it to you. And this is straight from your textbook, figure 13:18. So I have it fairly enlarged on your handout. And so we're going to label it. So before you start just copying stuff down, I want you to walk through it with me so we can make sense of it. So the first thing is, this is called the what? Cardiac cycle. We're looking at the cardiac cycle. We are going to overlay our EKG waves with physically what's happening to the volume and the pressure within each of our chambers. So if you're unable to see it, or maybe you want to, it is labeled the volume and the pressure. We're going to correlate this EKG wave with what's happening physically, pressure-wise, volume-wise, status-wise, with each of the chambers. And that would collectively be called the cardiac cycle. It's a cycle, so we can start anywhere we want, right? Whether the atria or whatever, right? But so we'll pick up when what is described as the ventricles being in mid to late diastole. So in this first little kind of piece of the highlighted area, you look at, we're basically looking at the area of the P wave. So if we look at the P wave, what are the atria doing? The atria are contracting. So over here where you see the little, first thing is, before we even add detail, generally the cardiac cycle is in reference to what's happening with the left ventricle. Okay? So when I talk about, or your book talks about mid to late diastole, it's talking about mid to late diastole of the left ventricle. So in the cardiac cycle, if I say mid to late diastole, actually the atria are in systole. Okay. So first thing is on this big pie chart, label it mid to late diastole. Are y'all okay? There's right here in this section during the P wave, the ventricle is in diastole. Are y'all with me? So during ventricular diastole, the atria are in systole. And that electrically with the EKG aligns with the P wave. So go ahead and just label the P wave. Was there an aha or a question?
Went on.
Oh. You should have said, oh, you were so excited. That's what you meant to say.
I was like, hey, it lines up. All right.
Good. So during the cardiac cycle, if I use the word mid to late diastole, I'm talking about the left ventricle. So if the left ventricle's beginning to finish up relaxation, the atria better be contracting and pushing blood from the atria down into the ventricles. So we're just saying go down in here. So the AV valve should be what? Open. And the semilunar valves to go to our different circuits should better be closed. So the first box, I thought I had it on here, but the first box is the AV valves. And so we're going to correlate the valves. The first row is the AV valves. The second valves would be the, you just say semilunar. And I already forgot the acronym, but that's good, I guess. Okay, so during ventricular mid to late diastole, we see we're correlating with the Pwave. And the atria are in systole. So the atria are pushing blood down into the ventricles. And so really we're adding blood to the ventricles. So the blood volume in the ventricles is what is it doing? What's happening? Mm-hmm. It's going to get a little bit fuller. If we're putting blood from the atria to the ventricle volume should be increasing. And you can see that here. This second plot, you can see the volume increase. So the volume in the left ventricle, or either of your ventricles, is filling up because the ventricle is relaxing, diastole, relaxing and filling. So you should see that volume increase. You may not be able to add it here, but I do have it enlarged in a second. But I'll just give you the acronym now because that'll fit better, and then I'll explain it in a minute. Right here where that volume maxes out, label that the EDV. I'll tell you what that, right where it maxes out. Right here. On this volume, we're going to label that the EDV. Okay? Now, we just wrapped up the Pwave. Now we've got to get into the QRS complex. The atria need to do what? They need to relax. They need to go into diastole. So up here, identify that the atria are in diastole. We don't see any arrows of forcing or pushing, anything like that. So they're relaxing. And the ventricles are entering systole. So during this highlighted area, say ventricles, or the second area, say ventricles entering systole. Entering it, but I'm gonna wrap it up. Takes a little bit. So during this QRS complex, the atria are in diastole. The ventricles are beginning to enter into systole. And when they finish their systole, what's going to happen to the blood? The blood volume? Yes. Stop. Yes, you guys are right. I'll set you up better. This is kind of dragged out a little bit, so when we get through that QRS complex, did everybody get to do the heart dissection, or did Thursday people miss out? Thursday people will get to miss out. Sorry about that. The ventricles are massive, right? So it's going to take a while to depolarize and repolarize all of those muscle cells, and we pick up that in the EKG. And so what happens is the contraction will go from the just like we talked about in the sequence, right? To go from this middle, right, to those bundle branches, and then the bottom to the up, so of the outer portion of the ventricles. And so we could get final contraction or systole of the ventricles as we went down the septum and now squishing on the outside up of the ventricles. When the ventricles fully complete systole, they have increased the pressure so much that we open up the what? By the time we contract, then yeah, we squeeze open the semilunar valves. We open them up. And so all that blood volume that we had in there just got pushed out where? To the body. So if it's coming from the right side, it would go to the lungs. Or if it's coming from the left side, it would go to the systemic circuit. And so our volume has dropped. So I want you to label this ESV. Right here we're labeling ESV. And again, just as before, on the next page we'll look at it. ESV. We're looking at volumes. Everybody catch where we're labeling that? The pressure will also change in the ventricles. In this line, the green plot is the ventricular pressure. So during the P wave, the ventricular pressure should be low because we're still adding blood to it. And then we squeeze on that volume of blood so the pressure goes up significantly, enough to open up our valves to let the blood go out. And then we send blood out, our volume goes down. And then we just repeat it over and over. And so it's a cycle. They could have drawn this in a circle, but it wouldn't align well here. So after systole, we go back into diastole of the ventricles. So label the last chunk over there, early ventricular diastole. Again, this should be labeled as figure 13, 18 in your textbook. This is correlating all the events of the cardiac cycle. We have 4 chambers to talk about, 2 that are like. And so, again, the reference is usually to the left ventricle, because the left ventricle is the one that sends blood out to our systemic circuit, which we can measure. Okay.
I have a question.
Yes.
Because I did do the heart perception, and the atria are so much smaller, like, how does it maintain the same volume, or does it not throughout the heart? The different sizes.
The volume will maintain the same throughout all the chambers. If there was a difference, you would have kind of a backlog of blood somewhere. And so what enters needs to match what exits. So the same volume enters the atria than does the ventricles. The reason we can get blood, the same volume of blood from those tiny atria to the ventricles and the same from the ventricles to our circuits is because the blood flow is coming on the at the atria at a decent enough pace, and then you also kind of have gravity on your side, if you will. And so blood is just going to naturally flow from the atria to the ventricles. It's going to, once it enters in there, it's going to flow in. And so it doesn't take much musculature to push what's left in there down into the ventricle. The ventricles, on the other hand, though, their open gate is on the top of the ventricle. And so we're not going to have that same type of flow in that case. And so that's why the ventricles need so much more muscle mass to pump that same volume, which we'll call stroke volume, out into the circuit. But also taken into consideration, atria to ventricle, I mean, you're looking at nanometers difference where that blood has to go. the distance that the blood in the left ventricle has to go, miles. Okay, so that plays into a factor as well. So the atria take the same volume and send out the same volume, but they have kind of flow on their side and the directionality, and the distance is null, basically. It's right there. So, great question. But you shouldn't see any disparaging difference in the volume entering the atria in the ventricles. Good question. Any other questions? Did I answer your question?
Yeah, because I just had this image of like a cup and bucket, you know, because it's so much bigger.
So a cup into a bucket and a cup out of the bucket. Should be the.
Which slices the T?
The T wave in this case traverses between so it's right here. So P, Q, R, S. This thing right here would be the T wave.
So number 4.
Yeah, or yes, aligning between 3 and 4 and crossing. Is that a light bulb coming on? All right. Additional questions before we move on? Let's do this every time. So if we turn the page and look in a little bit better detail of those images we kind of put our microscopes on to see, looking at figure 1320, specifically looking at the pressure changes in the ventricles. And do we have the atria? We don't have the atria shown in this case. But if we're looking at the cardiac cycle, here's a big thing, is when the ventricle's filling up, as it adds blood, the pressure goes up a little bit. But when those ventricles go into systole, the pressure significantly increases. So for example, what are we like at? 15, somewhere around there, up to about 110. So almost 100 millimeters of mercury pressure. Simply because the valves, the AV valves are closed and the semilunar valves are closed, and now we're squeezing on that volume of blood. So it's just the pressure goes up significantly, which is good because we have to open up the semilunar valves to keep the blood, get it propelled out into the circuit. And then overlaying this is the systemic circuit blood pressure. You'll notice in the aorta, the blood pressure is going to pulse, just like, if you were to take your pulse in your aorta like you did in your carotid artery, your arm, or whatever, the pressure will pulse. And if you notice, it's a little bit close to your blood pressure that you would measure. 120 over 80 is, here we have 110 over 10, or excuse me, over 70, excuse me. And so as the blood is pushed out in the aorta, the blood pressure spikes. And then after it ejects, it kind of drops a little bit. So if you were to correlate this to the first cardiovascular lab that we did, my abbreviation here, that highest pressure would be which? If I were to measure this out in your systemic circuit, that would be your systolic pressure. My abbreviation, your systolic pressure. The least amount of pressure that I can measure in my arteries would be the diastolic pressure. And then there's a third line in there. What pressure is that? What other pressure did we measure last? Mean arterial pressure. The mean arterial pressure, if you remember, we got to do this 2/3, 1/3 formula. We learned that our mean arterial pressure is closer to our diastolic than our systolic pressure, because the ventricle spends a little bit more, almost twice as much time in diastole than it does in systole. So again, we're labeling our systolic pressure, our diastolic pressure, and mean arterial pressure. Any questions thus far? All right, so this is the pressure changes that we would see in, say, the left ventricle. We can also look at the volume changes. I had you label them earlier, but let's talk about them a little bit. So again, looking at the blood volume in the left, specifically in the left ventricle, but the volume, right, would change. This is pretty similar, right, between each of our chambers. What did I have you guys label this first volume as? E. D. That stands for end diastolic volume. So the end diastolic volume is the volume of blood in the left ventricle at the end of diastole. So at the end of relaxation, it's filled up. So when it's done filling up, the volume is high, the greatest that it will be. And what did we label the bottom out? ESV. I'm going to give you one big stab at what that means. Very good. End systolic volume. At the end of systole, when we just contracted, our volume is probably low. It probably is not zero, like not 100% of the blood's going to be pushed out. So we could still measure it. So the end of systole, at the end of the ventricular systole, the volume in the ventricles is minimal. The difference between the two is our what? Stroke volume. Our stroke volume, if you remember by definition, is the volume of blood pumped out per beat. And so your stroke volume just accounts for how much was filled up, how much remains. The difference is how much goes where? Out to the systemic circuit. So again, the stroke volume is the volume of blood pumped out of the heart per beat. If you need help with that, that would have been 2 labs ago where we covered that, introduced it. We guesstimated it because we didn't want your lab partner opening up your heart and measuring stuff, right? No. But we can guesstimate it. Or if you had the ability to measure it with some new technology, you could get very precise actually measuring the volume of blood that passes through the heart. Does anybody remember how we guesstimated it? Your pulse pressure multiplied by 2 mils is how you guesstimate it. So before we move on, are you okay with using the word end diastolic volume being the greatest volume, end systolic volume being the least volume? And that difference between the two would be the stroke volume pushed out to the systemic, and to be honest, with the pulmonary circuit, the stroke volume going out into either circuit. Questions? The next thing that we can look at is the regulation of what's called the cardiac output. So before we start putting all these details in, let's define cardiac output. Let's review it from our lab. How do we define cardiac output?
Stroke volume times.
We do use the stroke volume.
Oh, rate.
The rate of volume, or I guess the rate of blood ejection, or the volume of blood ejection per what? Per minute. So the cardiac output is the volume of blood ejected from a ventricle per minute. Again, left ventricle kind of takes the cake on the work, famous bit. So a lot of people just say exclusively the left ventricle. So the cardiac output tells us the volume of blood pumped out by the left ventricle per minute. We need to know the what? Oh, it's given. Stroke volume and the heart rate and the pulse. So you calculate your cardiac output, if you want to abbreviate it, and let's just write the formula down. So it's just your stroke volume times your heart rate, or your pulse, or cardiac output is equivalent to your stroke volume times your heart rate. We measured it in milliliters per minute, but to be honest, in the clinical setting, you would convert that to liters per minute. And so, Lisa, this may lead into the question that you had: is that always the way it is? Okay, or can it change? And the answer is it can change. We quantitated it when we did our lab. In our lab we exercised and calculated the cardiac output at rest and after exercise. And so normally, right, under kind of full resting conditions, the pacemaker cells set the rhythm and all that for the heart. But you know, we can extrinsically override the heart. 2 primary, back to day 1, what can override the heart? The nervous system, the autonomic nervous system, which is down from the brain, and then also our endocrine system, right? So depending on what's going on in the body, extrinsically the nervous system or endocrine factors or other, you could probably even put humoral, right, if there's something extreme going on, can influence or alter the cardiac output. You don't have to be exercising for your cardiac output to go up. You could sit here and panic and realize that you didn't show up to class on Tuesday and you now realize you missed a test, right? What's going to happen to your cardiac output? It's going to increase, right? Because your heart rate's going up and, right, all kinds of stroke volumes going up. So you don't have to exercise, but that happened in that case under the nervous system. So the point is the cardiac output changes depending on your metabolic, right, demands at that moment in time. So it can be altered. Does that make sense? I hope it makes sense after talking about introducing this basically in January. So if we look at 1324, looking at the autonomic nervous system, highlighted in the purple would be our parasympathetic control, and then in the green, the sympathetic nervous system. So here's what I want you to add on that section about 1324. I want you to acknowledge that the sympathetic nervous system terminates in 3 primary places. The first would be at the SA node. So our sympathetic nerves terminate or end at the SA node, or you could say release neurotransmitter at the SA node, but also on the AB node. So the sympathetic nervous system can change the what? What do these things do? Our nodes change the rate of contraction, which influences the pulse. Sympathetic nervous system probably does what to your pulse? That tells those cells to generate action potentials even more frequently. Where else will the sympathetic nerves terminate? The ventricle myocardial cells. That just means the muscle of the ventricles. So the sympathetic nervous system can tell the ventricles to do what? What do these cells do? Do what? Contract more forcefully. Because the rate is controlled by the nodes, but we can directly increase the force of contraction by activating sympathetic nerves on the muscle cells. So more fast and more strong. So our stroke volume is probably going to go up, and our heart rate's going to go up, so our cardiac output will go up. So the sympathetic nerves terminate not only at the nodes to increase rate, but also at the ventricular myocardium to increase the force of contraction. And the word you would use is contractility. Did I say that earlier? Contractility. So increased contractility. if we increase the contractility, our stroke volume goes up. The parasympathetic nervous system terminates where? SA and AV nodes only. We do not see the parasympathetic nervous system acting on the, we don't see it acting on the ventricles. So your parasympathetic nervous system can only directly influence the what? The atria, which influences the rate. Those nodes. So under parasympathetic action, our rate goes down. Contractility, pretty average, right? It's not extra, so it's just kind of average. So heart rate goes down, contractility kind of low. So our cardiac output would be low under the control of the parasympathetic nervous system, which makes sense if you're sleeping at night. You don't need to distribute blood through your body like you're running a marathon. If you're not running a marathon, you're sleeping, so it'd be bad. Am I running a marathon this weekend? Is it this weekend? Sunday? Running? No? No runners? All right. I won't be there either. All right, so if we look at an alternative image of how these nerves act on the heart, at each of the nodes in the sympathetic nervous system also innervates the myocardium. The commands come down from the nervous system. It makes autonomic nervous system, but I like this image because it illustrates how the medulla oblongata is involved. So the commands do come originally from the medulla oblongata, and collectively they're called cardioaccelatory or cardioinhibitory. The accelatory would be which subdivision? Which cell? Sympathetic. Inhibitory would be the parasympathetic. So it all happens under autonomic control. What questions do you have about where this autonomic nervous system nerves control in different parts of the heart? That took us like 3 days to walk through a month ago, right? Parasympathetic. Now look at you guys, you're just applying it. So please acknowledge the progress that you guys are making. You're doing good. And then the next few figures illustrate chemically what's going on under the influence of the sympathetic nervous system on the nodes. So if you need to highlight on the nodes, epinephrine from our sympathetic nervous system activates the cell, or allowing it to do what? If I'm at the pacemaker cell and I wanted the sympathetic nervous system kick in, which of those pacemaker cells do more often? What am I opening up over there? Calcium, so the cell will depolarize. Okay. So in addition to the leaky channels doing their things, epinephrine, second messenger pathways, causes the cells to depolarize even more fast. Okay. So the SA nodes under the influence of sympathetic epinephrine will depolarize more frequently. The connection you guys made earlier, the heart rate goes faster, it goes increasing, it goes up. So this is at the SA node, right? We allow it to depolarize more quickly under the influence of epinephrine. What is the parasympathetic nervous system? So not norepinephrine, but we'll see which neurotransmitter. Acetylcholine from the vagus nerve, parasympathetic nervous system will cause these cells to do what? Parasympathetic nervous system. So what do these cells need to do? Look at the ion. they're going to hyperpolarize so that their action potentials become less frequent or decrease. So again, the parasympathetic at the nodal cells, the SA node, the AV node, actually causes those cells to hyperpolarize, decreasing their chance of reaching threshold, right, less often, right? So it slows them down. So the heart rate is less frequent. It won't turn it off unless there's a disease.
Is that the SA node again?
SA or AV node, both. Yes. But it could happen. We gave it a scenario when we talked about the vagus nerve in the central nervous system, and medics, right? Vagal. What do they call? How do y'all say it? It's probably a late term. I don't know. Like vagued out. Y'all say that? Someone has vagal tone. Nobody. We're not making this all over. Someone's heart rate is so low, they may do the vagus nerve, the heart rate goes down, they go to cardiac arrest or die. The scenario I gave it, at least in one of the lives we're talking about Elvis Presley, and again, everybody's like, who's that? Yes, people looked at me like I was crazy. I was like, oh my gosh.
I think that maybe the deeper thing.
Do what? Well.
Yeah, tell us about it.
So the vagus nerve, if you remember, the wandering nerve, right? It wanders beyond the head and neck region and also through the abdominal cavity. And so when someone has to go to the bathroom and it's not working right, bear down, right? You push on that vagus nerve and it stimulates it to release what? The acetylcholine, which causes hyperpolarization at your node, so your heart rate goes down or maybe even off. Okay, so then the heart's not beating.
Just
Do
like
what?
going to the
That's what
bathroom?
happened?
What do you say?
Yeah, he does it on plot.
I understand that, yeah. I mean, why they don't
That's what it
really
was.
but yeah, it wasn't.
They found him, he was like down in front of it, like he looked like he was
back
frantic.
up.
He died like jumping off the building.
Just saying by using the bathroom,
They tried to like,
you're saying the heart would stop, that's what you're
we've
saying.
gone like in all.
And if the pressure is so great in the abdominal cavity that it
Not healthy.
activates the vagus nerve so much, sure, you can pass out or don't strain. Yeah, so the question, the clarification was, am I at risk of dying if I go to the bathroom? Okay, so if there's no other medical condition intervening, right, probably okay, but generally there's some other prevailing condition.
He
like
wasn't very healthy whenever he passed
Like
away,
drugs
so.
could have done that maybe then? Like, I mean, yeah, drugs are gonna mess with the whole system, and so it's just a spiral. Yeah, he was a big boy.
I read somewhere he was on like all Jello diet, like he would only eat Jello. And someone said jelly bean sandwiches too.
No, you're better jelly than me in the fries.
That's right.
Yeah.
Yeah.
That was his big. What?
So back on track, action potentials, SA no. Figure 1326 quantitates the difference between the action potential conduction. They're overlapping it, so hopefully you can kind of take away. In the gray is at normal rest. Okay, so we can see it hitting at 4 milliseconds, and then again at 4 tenths of a second, and then 1 and 2 seconds. Right, so you can see the distance. Okay, so 8 seconds to 8 tenths of a second normally, which would align with your R-to-R intervals that you guys measured, the EKG, if you're in the Tuesday or Wednesday lab. Now, the action potential rate does what as the sympathetic nervous system activates? More frequent. And so, right, we can see them becoming more frequently. So you can see, it's going to mess with my eyes a little bit, but under rest we see 1, 2, right? And then under sympathetic, how many do we see? 1, 2, 3. And what about the parasympathetic? The rate will go down, so we just see one little plot. And that aligns exactly to what we've been talking about the last few minutes. The sympathetic nervous system speeds up the rate of action potential conduction by causing the cells to depolarize, whereas the parasympathetic nervous system slows them down by causing those cells to hypopolarize. Y'all, is it making some sense? All right, so as we know from our lab experiment, we know that the stroke volume can actually change, and even just a moment's notice by changing physically what's happening within your body. And there's three primary ways in which the stroke volume can be altered. They include ventricular contractility, I'll review that in just a moment, changing the end diastolic volume, and then changing also what's called the afterload, a word which we've not seen before. So let's first just talk about contractility. What does the term contractility mean?
The force of contraction.
The force or the strength of contraction. So if a ventricle has greater contractility, the force is greater, so our stroke volume should go up. So there's a direct correlation between contractility and stroke volume. The stronger the heart beats, the more blood it can push out, the more contractility. And the reverse would be true, right? If my heart beats like I'm taking a nap, my stroke volume is going to be low. So it's directly related. Another thing that influences the stroke volume is just simply how much blood enters. That end diastolic volume is going to have a very big influence on the stroke volume. Correlation is also very the end diastolic volume and the stroke volume are what type of relationship? Direct. Or, yeah, they're direct with one another. So if my end diastolic, what I send in is high, what I send out is probably also high. So there's a direct correlation. If there's more blood coming in, and it goes back to the question earlier, does that change? Sure. But if there's more blood coming into the ventricle, there was more blood coming into the atrium. I want to add something here about the end diastolic volume is the more end diastolic volume there is, the more the ventricle stretches. So if you have a greater end diastolic volume, the chamber stretches even more. I mean, kind of like a balloon, right? If I were to put in a water balloon, if I were to put in 1 milliliter of water versus 500 milliliters of water, right? In the second scenario, it's going to stretch more than in the first scenario. The same thing is analogous here. In the ventricles, the more blood you put in, the greater the end diastolic volume, the more that heart stretches out. The more it stretches out, we look back to what? Contractility. So actually, contractility is dependent upon that end, also dependent upon the end diastolic volume. So put more blood in, increase contraction, increases stroke volume. The third thing that we've not talked about before is called afterload. And this one ties into, if you remember, there's a period of time when the ventricles, they've taken in their end diastolic volume, and they're squeezing on that volume of blood, and our pressure's going up. Do you remember that? We saw that huge spike. But all 4 valves are closed. The pressure's going up. Okay? And so that means is the ventricles have to generate a bunch of pressure to push the blood out. Okay? To add on to that, they're going to open the valves to go to the systemic or the pulmonary circuit. Okay? But once the blood gets pushed out, it's over there. Right? So it's at risk to doing what? Flowing backwards. And so not only does the ventricle have to generate enough pressure to get the blood out, it's got to generate enough blood pressure to make sure it keeps going in that direction. Does that make sense? Yes, it's got to push on it. And so that natural tendency, so if you can go with me in my visual, I'm hurting you guys in my brain here, through this door, right? Y'all would be the blood through the ventricle, right? If I wanted to push you out the door, and there was some people over there, there were other people on the next class is chomping at the bit to get in. I need to generate enough force to not only get you guys out, but through the other guys, the previous stroke one. Because naturally they would want to all try to push the bum rush back into the building, right? And so the afterload is that backward pressure, the other people trying to get in when you're trying to get out. Does that visual help? So the afterload is that backward pressure that's out on either the pulmonary or the systemic circuit that the ventricles have to oppose to get out. Question? The afterload is that opposing pressure to the exit of the blood out of the ventricle. Again, the afterload is that opposing pressure to the stroke volume exiting the ventricle. So what's the relationship between afterload and stroke volume? If my afterload goes up, my stroke volume goes down. If there's 500 people out there trying to get in, and you guys trying to get out, they're probably going to win, right? If there's 2 people out there and you guys are trying to get out, the afterload is less. Right? The probability of you exiting is better. So it's inverse. So these are the 3 things that have a direct influence on changing the stroke volume. This is summarized in another image. Oh, excuse me. Figure 1327 helps visualize contractility. So right where it says contractility, say, write a note, see figure 1327 or see below. We know that in our muscle cells, in the myocardial cells, epinephrine, norepinephrine allow the cells to activate their contraction or increase contractility. So this image is now looking at the myocardial cells, where earlier we're looking at the pacemaker cells. Am I okay? Increases contractility. Summarized there. And then if we look at another image, you have a similar one called figure 1331. This is going to summarize where we've been. I just like this picture better than using it. So if we're looking at cardiac output, you should recall that it's a product of our stroke volume times our heart rate, right? You know that the heart rate can change by both sympathetic and parasympathetic nervous system. The sympathetic nervous system causes those pacemaker cells to depolarize more frequently. By contrast, the parasympathetic nervous system causes the cells to depolarize, or actually calls them hyperpolarize, so they're not generating activity. So sympathetic nervous system does what to heart rate? Increases. The parasympathetic nervous system decreases. And hence the dashed line. Inhibitory. This image also helps us summarize that not only does the sympathetic nervous system act on the nodes, it also acts on the what? Contractile cells. To directly influence contractility, which directly influences stroke volume. If your stroke volume goes up, so does your in diastolic volume, and your stroke volume goes. So there's several factors that influence your stroke volume. We can change the heart rate for sure, directly, but we can also use the sympathetic nervous system to increase our stroke volume. By changing that contractility, that preload in diastolic volume, and then even if the afterload gets too high, that mean arterial pressure goes up. What would happen? If everything goes up, back pressure goes up, our stroke volume would go down. And your body will continue to do this, maintaining your pressure where? In your cardiac output, your heart rate, stroke volume in your body's set point, even this set point. So depending on what's going on, sleeping, exercising, whatever, micromanagement going on this factor. What questions do you have over the materials we covered for chapter 13? Yes.
So the sympathetic nerves speed up and depolarize, and the parasympathetic nerves slow down and
Because they're hyperpolarizing. The nodes are hyperpolarizing. I want to introduce chapter 14 by going over your handout that you're going to turn in just a moment. In the handout, I had you just label. And so on the bottom of the handout, we'll talk about some functions. And that'll help next week go a little bit smoother. Chapter 14, we're going to look at blood vessels and blood pressure. And then chapter 15, we'll look at blood. Hopefully we'll get through chapter 14 on Tuesday. Hopefully, I don't know if we'll get into 15, but I want to introduce the respiratory system next week. So chapters 16 and 17. If we look at the circulatory system, our blood vessels, there are three major types of blood vessels. The first we know are called what? Arteries. We also have veins. And intermediate, we have capillaries. In this image, on the far left-hand side are the arteries, and on the far right, the veins. Now, what do the arteries do?
Bring oxygenated blood from the heart to the body.
Let's take out the amount of oxygen, but they take blood away from the heart. The oxygen content, the nutrient content, hormone content depends if it's been to the systemic circuit or if it's going to the pulmonary, wherever, right? So, but if we were just to strip away any details, arteries carry blood away from the heart, while veins carry blood to the heart. Arteries carry blood away from the heart. Veins carry blood, return blood to the heart. Intermediate are the capillaries. What do the capillaries do? Exchange between our tissues and the blood. We introduced this way back in the beginning of the semester, acknowledging that there's an exchange between the blood plasma and the interstitial fluid. And the interstitial fluid, the plasma. So on your capillary, I want you to draw an arrow of fluid pushing out. So you're going to draw it here or here where fluid is being pushed out. What term did we use to describe this outward movement of blood plasma to the interstitial fluid? Which one? So everything together would be called bulk flow, but specifically if something's going out of the capillary to the interstitial fluid, filtration. Very good. So draw an arrow of fluid exiting a capillary, outward arrow. Not so much through the capillary as out of the capillary. Does that make sense? It's coming from here, from the lumen of the capillary to the surrounding tissue, which is not shown. So I would draw something. So I would draw a little fluid coming out from the capillary. It's leaking. Do you remember from your pre-lat or your handout? It's leaky, right? So we would call that filtration, a term we became introduced to in chapter 5. So our capillaries can filter substances out, but what else can they do? They can absorb or reabsorb, where products are moving into the capillary. I'm going to put that word over here. Reabsorb. Anatomically wise, I want you to notice the diameter of the lumen of each artery in the vein are large, but what? Which one's larger? The lumen of the two vessels, which one is larger? The lumen is the middle fifth. So the veins have a larger lumen diameter when contrasted to the arteries. So you're just over there somewhere. Lumens have larger, veins have larger diameter lumens. Sorry. All right, so what we'll do on Tuesday is we'll pick up here in blood vessel structure and talk about blood pressure, blood, etc. that you guys had a nice introduction to with your handout. So go ahead and turn in your handouts, and we'll see you guys on Tuesday.